This is a question from your lab assignment, section 6.4. A heavy rope, 50 feet long, weighs 0.6 pounds per foot and hangs over the edge of a building 120 feet high. Approximate the work required by a Riemann sum and then express the work as an integral and evaluate it. So there's two questions here. How much work is done by pulling the rope to the top of the building? And the second one is how much work to be done by pulling half of the rope to the top of the building. All right, let's begin. So this is the picture that I got. And this is the building. We got the big building, and then we have the rope hanging over the side of it. And then the convention is to let your x-axis be pointing downwards. So the 0 mark would be at the top of the building, and then as you go down you're looking at positive x values. The rope weighs 0.6 pounds per foot, and so what we're going to want to do is take a piece of that rope, like a delta x piece of that rope, and then figure out how much work it's going to take for this small piece to go up to the top. And then so if we break this up to a lot of little pieces, then we're going to get that Riemann sum, and then it will become our integral. So a small piece of that is going to be a weight. It weighs 0.6 pounds per foot. And so we're looking at delta x is the amount of feet that we're looking at, delta x feet, and so this is just going to be 0.6. So they made it into a fraction, but that's all good. Let's move on. If a portion must be lifted delta x sub I feet, then the work done is going to be if this is delta x, and then imagine the length or the distance that it has to travel is delta x, or I'm sorry, the piece of the rope that we're looking at is delta x feet long, and we found that the weight or the force is going to be 3/5 times delta x, and then so that's the force. The weight is the force in feet, or in pounds, and then now we have to travel we have to travel x sub I star feet up in the air. That's going to be the distance. So our work that it's going to take is going to be 3/5 delta x times x sub I star. So we just put 3/5 in here, or 0.6, but they wanted a fraction, so 3/5 times delta x sub I star, or I'm sorry, 3/5 times x sub I star times delta x. So that is the amount of work for this little piece to go up. And so we're going to add them all up, and so this is going to just continue to be 3/5 times delta xi 3/5 times x sub I star times delta x, and then we're going to add up all the little pieces over here, and so our Riemann sum will become an integral. So the rope is 50 feet long, and so we're going to want all of that rope to go all the way up, and then we're going to have 3/5 times our delta x will become a dx, and our x sub I star will just become an x. And so here's our integral from 0 to 50 of 3/5 x dx. And so to integrate that, we need the integral of this, 3/5 times x. The integral is going to be x squared over 2 times 3/5, so this is 3/10 x squared, going from 50, or 0 to 50. 0 is going to be gone, so 50 squared is going to be, this is going to be 3 times 50 squared. 50 squared is 2500, and then divided by 10. So we can knock off a 0 here, and then we can just multiply this. 250 times 3, I think it's 750. So it's going to take 750 foot-pounds for it to climb up there. All right. So now, what if we're only pulling half of the rope? Then this whole delta X business that we're doing here would really only apply for half of that rope. And then the other part of the rope, down here would just be carried along. And so let's take a look at how they approach this, and then maybe it'll help us do our homework assignment. We take the rope into two pieces: the work needed to lift the top half of the rope, and the work needed to lift the bottom half of the rope. So the work done to lift the top half of the rope is as follows. It's the same thing as part A, except instead of going all the way to 50, we're only going to take 25. So we go through this motion over here. The derivative, like we saw before, was 3/10 times x squared, except now instead of putting 50 in there, we're going to put 25. So I'm going to need to know what 25 squared is, and I think that's 625 times 3. So I think this is going to be 1875 divided by 10. Enter a fraction, integer, or exact decimal. So I think that'll work. Or suppose we can put a decimal and make it 187.5. Now if we compare that to 750, it looks like it's a lot less work. First of all, we know it's less work because we're only pulling up half of the rope. A lot less, well, that's because the bottom isn't accounted for yet, and so we'll keep that in mind. So let's check our answer here. That all looks good. Now the bottom half of the rope is going to be a constant force. So there's 25 feet of rope, and remember that the rope weighs 0.6 pounds per foot. So to find the weight, it's going to be 0.6 pounds per foot times 25 feet, and so that's going to come out to be pounds. And I think if we do this multiplication, it'll end up being equal to 15 pounds. So that's 15 pounds. We really just need to multiply this by 25 because it's gonna, this whole yellow piece over here, it's gonna move up 25 feet up in the air, and it's not gonna go on the top of the building like the rest of the rope. It's just gonna keep hanging down there. So it's really just 15 times 25. So 15 times 25 is, I believe it's 375. You can do this integral. This is going to be 15x evaluated at 25 and 50, and then you'll see that you'll get the same result. Okay. So we have 375 divided by 2 foot-pounds for the top half of the rope, and then 375 for the bottom half of the rope. And so let's see if we can add that together. And I think I get 562.5. Now, if we compare that to 750 for pulling the rope all the way up, and this is a lot, not a lot less anymore. It's considerably less, but not as much as it was before. So I think this answer makes sense. So let's submit it. And then that's it. All right, so the tricky part here is for the second part, we're going to treat the bottom half of the rope as being constant. And so we did a simple force times distance calculation, and we didn't really need to do this integral if you're just lifting up a constant. The first part was not constant because we need to, after it goes up to the top of the building, then we're not going to consider any more work being done. All right, I hope that helps.